In this video, I'm going to talk about how we can arrive at key equations involving the relationship between the cell potential and free energy for an electrochemical cell, and also the Nernst equation, which is an equation that allows us to calculate cell potential under non-standard conditions from cell potential under standard conditions. So if the overall reaction done in an electrochemical cell is thermodynamically allowed, then that means that it's going to release energy. And that energy is going to be carried by the electrons. And so we measure that energy in terms of something called a potential. And potential is measured in volts. A volt is equal to a joule per coulomb. So the joules represent the total amount of energy that was released by your reaction. And the coulomb represents the charge of the electrons, the total charge of the electrons that were carrying that energy. So the total charge of the electrons that were traveling from the oxidation half reaction to the reduction half reaction in your electrochemical cell. And so joules is the energy and coulombs is the charge of the electrons. And because we're measuring that in energy per quantity of electrons, it means that it's an intensive property. If we do the reaction on twice as much material, it's still going to be the same amount of energy carried per coulomb of electrons. It's probably worth noting that there are other terms that can be used to mean potential. The word voltage for obvious reasons, but also electromotive force and electric potential difference are other ways that various sources will use to describe potential. So how does potential relate to free energy? Well, we need to start by going back to the first law of thermodynamics, which says that any energy change is going to have to happen as a combination of heat and work. And if we're talking about a reversible process, then the heat and the work would also need to be reversible. Electrochemical cells are typically performed at constant temperature and pressure, and as such, the heat term is going to be equal to your enthalpy change, because recall that enthalpy is heat at a constant pressure. And the work term can be divided into two subcategories. There's pressure volume work, which typically involves the expansion or compression of a gas. And there's non-pressure volume work, which is all the rest. The work done by an electrochemical cell does not involve expansion or compression of a gas, and so it is therefore non-pressure volume work. As it turns out, the non-pressure volume work done on an electrochemical cell is equal to enthalpy change minus temperature times entropy change. And this portion of the equation over here ought to look very familiar to you, because it's half of an equation we've used a lot so far this semester, the equation relating free energy to enthalpy and entropy changes. And so we can therefore conclude that the reversible non-pressure volume work done on an electrochemical cell by the surroundings is equal to the free energy change for that reaction. But again, remember, this is work done on the system by the surroundings. We're not interested in the work that's done on the system by the surroundings. We're interested in the work that's done by the system on the surroundings. But that's okay, because it's very easy to get from one to the other. If the system did 2 units of work on the surroundings, then that means that the surroundings did negative 2 units of work on the system. Similarly, if the system did negative 2 units of work on the surroundings, then that means that the surroundings did 2 units of work on the system. It's the same number, we just switch the sign because we're switching the perspective. And so therefore, the maximum amount of non-pressure volume work that can be done by the system on the surroundings is equal to negative free energy change for that reaction. So the work that's done on the electrons in an electrochemical cell is going to be a function of both the charge of those electrons and the potential difference that they're having to move through. And so we can say that the work is equal to that charge times the potential difference. Now, the charge of the electrons is going to be equal to the number of moles of electrons times the charge per mole of electrons, Faraday's constant, 96,485 coulombs per mole. And of course, electrons have a negative charge. And we could therefore say that the free energy change for our reaction will be equal to negative moles of electrons times Faraday's constant times cell potential. Now, if we were to plug units in to this version of the equation here, we would have moles times coulombs per mole times joules per coulomb. And our moles would cancel and our coulombs would cancel, and we'd be left with a free energy value in joules. But most of the free energy values on our tables are in kilojoules per mole. And so if we would prefer not to have the moles cancel, if we would prefer to get free energy values in joules per mole or kilojoules per mole, then what we can do is, instead of using the number of moles of electrons, we instead use something called the stoichiometric coefficient, which is simply the number of moles divided by 1 mole. It's almost kind of like the activity of the number of electrons. And so if we do that and write out the equation like so, then we don't have any units for a stoichiometric coefficient. That gets multiplied by coulombs per mole, which gets multiplied by joules per coulomb. Now, with this version of the equation, we get free energy values out in units of joules per mole, which are easily converted to kilojoules per mole, which are completely compatible with all of the free energy values in all of the standard thermodynamic tables. And for that reason, we will be using the stoichiometric coefficient rather than n for the number of moles. It is also very important to note the role of this little negative sign here. It means that the signs of the cell potential and the free energy change for the reaction will always be opposite, because the stoichiometric coefficient has to be a positive whole number, and Faraday's constant is 96,485. And so the effect of that negative sign is to ensure that the cell potential and the free energy change always have opposite signs. This means that reactions that are thermodynamically allowed, which have negative free energy changes, will have positive cell potentials and vice versa. So if the free energy change for a reaction is equal to negative stoichiometric coefficient times Faraday's constant times cell potential, it is therefore reasonable for us to conclude that standard free energy change for a reaction is going to equal negative stoichiometric coefficient times Faraday's constant times standard cell potential. And we recall our central equation relating standard free energy to free energy under non-standard conditions. Delta G equals delta G naught plus RT ln Q. We can substitute in these two equations at the top to translate that equation into one that, instead of free energies, refers to cell potentials. And so I can say that negative stoichiometric coefficient times Faraday's constant times cell potential is equal to negative stoichiometric coefficient times Faraday's constant times standard cell potential plus ideal gas constant times temperature times natural logarithm of reaction quotient. And I can then divide everything by negative stoichiometric coefficient and Faraday's constant. And that's going to get me cell potential is equal to standard cell potential minus RT over stoichiometric coefficient times F, all times natural logarithm of Q, which is the equation in the box, which is the Nernst equation. And so if we add those new equations to our equation map, we can see that we have now added two more ways to get to the central terms of free energy change and standard free energy change. And if there was any way I could possibly have fit an arrow in to do so, I would have also noted that reaction quotient is an important tie to the cell potential under non-standard conditions because it shows up in the Nernst equation, but I reached the limits of what I could physically fit on one page.